All right, I think we are live. Hopefully my video's all right. I've been running a lot of load tests lately, and I think I've messed up my network card, so I don't. It's been going in and out, so fair warning. Stephen knows this because I was I was all over the place yesterday. Yeah, so thanks for joining. Today we got Steven and Aaron, and then we have a special guest, Michael, who doesn't usually join us, who will be when we talk about all of the ACP stuff that's been going on. He posted an interesting ACP that he'll cover. But first off, we'll go right into the release that was put out last night.
Cool.
So, Kyle, if you can share my screen real quick, thanks. All right.
Yeah, so this was really a another like big post Durango cleanup. But one of the nice things about this cleanup is it actually disables some of the legacy gossip. So we've talked in the last call, I think, a lot about like transaction gossip and things like that. So this actually disables two different places that we did gossip. One is the peer list gossip for P2P connectivity, and then the other is for block acceptance, specifically for non-validators. We used to explicitly push accepted blocks to peers in the network so that non-validators or low-staked validators were able to hear them efficiently. But we no longer needed to do that because now that Durango is out, everyone is performing the pull gossip. So on the consensus side, they will periodically send a pull query. And then on the P2P networking side for peer list, they will periodically send a get peer list message with a Bloom filter. So I know we were looking at the bandwidth savings here, and I think it was at least 30% of the bandwidth we were seeing for non-validators was these two legacy forms of gossip. So it should be a significant bandwidth reduction updating to this release. So that's really nice. And then the kind of the other cornerstone of this release is introducing another form of sampling for the transaction gossip, which is sampling by stake. So we we found that because of the size of the primary network validator set, sampling uniformly is good for disseminating, transactions to all of the validators, but not necessarily the best for managing bandwidth and time to finality. So now, in addition to sampling uniformly from the validator set, we will also always send transactions to the top 90% of stake, which on the P chain pretty consistently makes the time to finality for transactions on the public API around a second and a half or so based off of my random testing. So pretty significant time to finality improvement on the P chain. And this is, of course, on all three chains, P, X, and C. C is probably going to have a bit different performance just because there is an existing mempool there and consistently blocks being produced. So different times maybe for different chains, but on the P chain, I think we're really happy with that time to finality for as an end-to-end user issuing transactions. So
That's what I was going to
um,
clarify. That's from your end machine start to finish issue to get the transaction back. Yeah.
yeah. Yeah, so I don't know if there's anything else that people really want to talk about for this release. There was a lot of cleanup. I don't remember the diff, but it might have been more deleted than added, which is always a sign of a good release, in my opinion. Um, but yeah, I don't know if there's anything else people want to chat about.
Yeah, to give you some sense, like the joke we had internally is like we were excited for Durango for a lot of features and whatever, but we were excited for Durango because of all the code we could delete. And so we are on the other side of that threshold now. So we were pretty excited about seeing all this go live and seeing everything. And I think the only other thing I wanted to call out was I think one of the late ACPs that got in pretty late relative to the others was ACP 62, which was the BLS enforcement for staking going forward. And the impact of that, even only a few weeks later, has been pretty immense. I think there's now it's something like 48% of all validators have a registered BLS key. So you may say, cool, like if I'm a subnet, I guess that's useful, but otherwise, like I don't get why I need it. There are a number of interesting improvements coming or planned for the primary network that take advantage of those BLS keys to make consensus or like basically voting on rewards more efficient and potentially allow like subnets in the primary network to interact in new and interesting ways, which we will talk about kind of towards the end with the ACP stuff. But just wanted to share that that is going pretty cool, I think. The other thing I wanted to call out is we've been working with a group called Antithesis to better test the engine and sort of like distributed load testing environments. Or deterministic load testing environments. And so we're getting things squared away there. So if you see that, that's also what that is. Yeah. Anything you wanted to add, Aaron? I don't know on the core ETH side if you're familiar with anything. Oh, I guess we updated some of the dependencies there. I know Daryush and Jay have been driving that.
Yeah, no, nothing from my side.
Cool. Yeah, mostly cleanup. Recommend you update just because it, a lot less code that's unused is in the code base, and it also, especially if you're an RPC provider, will help with anyone like transaction time to finality for anyone that submits transactions to you. So that is a good change for you. So yeah, I think with that we can switch back over to the roadmap. So let me stop my screen share, present my screen share. Let me know if that works. I got the actual PNG this time, so it should be easier than like sharing what was like a Twitter screenshot or something I was doing last time. Is that easier to see? I don't know. Hopefully. Can you see that, or is it? I'm going to zoom in when we talk about certain parts. Don't worry.
Yeah, you can see that. It's a little grainy. I think that's just your network card, though.
Yeah. It turns out, like, I digress
It was
again, but like,
it was so funny. It was so funny. Him like trying to sign the Mac build for the release yesterday. Just random networking
yeah. So like,
errors and
I
like
was, I was getting errors I've never seen before, which was like, imagine uploading a file somewhere, like on the command line, and then your computer just seg faults and says like bad bus. Like, clearly I wore something out. I don't know what happened. And then I tried to upload a file somewhere else, like to Google Drive or whatever, and it just gets 35, like 33%, and then just stops. Like something's wrong. And then like yeah,
the
nonetheless.
best
So
part is as he was talking to me about this over at Google Meet, like his screen just freezes for like 10 seconds. Just like oh yeah.
fuck. Yeah, so it turns out like I found that like I don't think no offense to the Apple engineers here, but like I don't know how much these network cards are tested with like sustained like multi-hundred megabyte like egress and like what that might do to the chips. But yeah. We're back to the roadmap. So yeah, so I think last time we talked a good bit about bricks and what's coming there. So we're working on producing this reproducible load test right now with the Vrix POC. And so we're really hoping to get that out soon. I think one of the inspirations there is, anyone that's on Twitter, you know, is familiar with this concept of like, hey, like we hit, whatever 1,000 TPS, like here's a picture of it. It was sick. Like it should have been there. So the point with this reproducible CLI test is we're going to hit a number, hopefully that we're happy about, and then we're going to release a script, single script, nothing else. You have to do anything. You don't have to go anywhere. If you have an AWS account, it will reproduce exactly what we reproduced, barring any modulo any bugs that cause it to not hit that. But like the if it's assuming it stays stable, that's what you'll get. And we want to enforce that standard for all of our testing with performance because I think it's become such a big marketing thing that like we really want to be clear and precise about the things that we're doing under certain scenarios, right? Like if you change the workload, you change the regional distribution, you change the machine type, all of those things will change. So the important part here is to give people that are adopting the Hyper SDK a very clear idea of what sort of performance they could get underneath certain distributions or certain sort of machine types, which is really all that matters here. The customers that we're talking to that want to use this, it's very much a question of what sort of like price performance ratio I'm going to get with this. So that's what we're trying to do. And then, as we've mentioned before, you can go, into the sunset trying to get infinite TPS. We're going to stop at the 100,000 target and then say that's good enough for now. So we're not going to get into a arms race with that number. We're just trying to get a single subnet to that performance, and then we plan to hopefully allow it to scale more with CPU, but it will not be our focus in the short term to get that ever higher. So yeah, that's what we've been working on. So there's a few pieces that fit into this. And then the big point where people should be able to build on the Hyper SDK is when we get to this integration ready checkpoint. The integration ready checkpoint is basically saying that the interface for virtual machine builders should be relatively stable. But if you try to build it at that time, it may things you can obviously get started, but like the interface is not stable. So like you may from release to release break. But obviously that will change hopefully at this point. But yeah, so that's the just quick recap on what we were talking about brick stuff. And so now we'll go into the consensus, optimization work. So I'll turn over to Stephen and Aaron on this one, and let me know if you want me to move around or zoom in or whatever.
I'll let Aaron, how do you want to start here? What do you want to talk about?
Well, we haven't put the paper out yet, so I don't know if we want to talk about some of the ideas there. I think, I don't know. What do you want to talk about? I think your stuff is public, so maybe we talk about that first, the bootstrapping optimizations.
Yeah, so I have been working on basically optimizing the bootstrapping fetch times recently. So the way that bootstrapping currently works is pretty network latency bound. So specifically, we do this kind of initial syncable, like recently accepted block that we fetch by like querying validators and determining like a recently accepted block. And then we basically follow parent IDs back towards Genesis. And we don't just go like one at a time because that'd be like really network latency bound, but we will essentially say, okay, here's the parent ID, give me like some number of ancestors of that parent ID, they'll stream you those ancestors, and then you get that and then you continue on. The issue with that is it's a very single like fetching process, and this definitely does not fully utilize network bandwidth. So if someone is bootstrapping Avalanche Go right now, like on say like the P chain, X chain, or C chain without state sync enabled on the C chain, they'll notice that like their bandwidth utilization and their disk utilization is like really not increasing that quickly. And which doesn't really make that much sense. If you're downloading stuff, it should be bottlenecked either by your disk or by bandwidth, one of the two. So the way that we are hoping to improve this is by a couple of things. So the first thing that we definitely want to do is have multiple concurrent fetches going on at the same time. So an easy way to do that is essentially just rather than syncing at a single point, sync at like multiple points. So now all of a sudden you're going to just multiply your bandwidth utilization by however many points you're syncing to. And so at that point, you should be able to theoretically saturate your bandwidth. Now, it turns out if we do that, we very quickly run into a disk bottleneck because our chain syncing mechanism for like keeping track of what needs to be synced and what's executable and what isn't was just a fully reused portion from the DAG syncing. Now, the DAG logic is way more complicated because you have transaction dependencies mixed with vertex dependencies, which are nonlinear. So like heights aren't particularly useful to track here. And it turns out that you can't just really easily check like, oh, do I already have this? That ends up actually performing disk reads on whether or not you already have a vertex, things like that. So what you can end up doing in a chain world that's super nice is essentially implement an interval tree that keeps track of the intervals that you've already synced, and you can very efficiently manage that in memory with a on-disk backing if you restart. And so now all of a sudden, rather than performing all of these disk reads during bootstrapping to check whether or not you need to continue fetching or not, you can have this really efficient in-memory structure that results in essentially when you're downloading stuff, you have a very simple couple of writes into your disk, and now your bottleneck is back into basically a different part of the code. So it turns out that the easiest way for me to do this was actually implement that second, or patch that second bottleneck first. So there's a few PRs implementing this kind of on-disk interval tree that will hopefully get into 1.11.4. And then we will probably continue on with implementing that concurrent fetching as well. Maybe in 1.11.4, maybe in 1.11.5. But I'm really excited about this. It turns out after these two bottlenecks, it goes into peer selection. So basically optimizing for like which peers are willing to give you the most bandwidth to actually like provide those blocks as kind of the next step to further optimize because and yeah, so we actually already have some modules for that for the C-chain state sync and also the MerkleDB experimental sync use basically a bandwidth tracking module for optimizing for fetch times. So we'll be incorporating that into the bootstrapping logic as well. So I think with those three things, we should see a significant improvement for the fetch times for historical blocks. And then the kind of last step, which might be a little bit further off, would be around executing blocks while we are still fetching historical blocks. The reason that that's a little bit further off, perhaps, is because it probably fits best in with the concurrent consensus engine work, which is in and of itself a large endeavor to basically support concurrent pull query, push query, and shit like processing and handling and like concurrent block execution. So that might be a little bit further off. Definitely might not go into 1.11.4 or 5, but that's kind of the ongoing kind of practical optimizations that we're working on in the consensus code right now. So I'm really happy about how the interval tree came out. We have like some of these parts in the consensus code that I would say are like as the time goes on becoming more and more black magic as like additional constraints pop up and like we patch this thing and like this thing was implemented like 4 years ago and like the number of people that have any idea what's going on there is dwindling down to single digit numbers for sure and sometimes towards zero. So this will be a really great kind of cleanup for both maintainability, performance, and kind of helping along our future improvements. So yeah, I think that's really all I wanted to say on the bootstrapping side. Yeah.
Yeah, so one other thing that blends together the bootstrapping side with some of the ACP work, and I'll actually reference one that hasn't been published yet, but is still a work in progress, is the way that we're doing this bootstrapping improvement is, as Steven said, we want to parallelize what we're able to bootstrap. And the way we do that for the C-chain, P-chain, and X-chain, all of these network blockchains in the primary network is what we do is we start out with some block, which is the last accepted block reported by the network. And from there, we sort of traverse backwards right now, where we say, okay, well, what's the parent? And then we say, okay, well, we can fetch that one's parents. And so we end up, in order to fetch back to any block in the history, we have to go one at a time. And so the optimization that allows us to parallelize this for the primary network is we're going to hard code what are the blocks that have already been accepted by the network. And so we can do this for the networks that we sort of maintain, the XP and C chain, because we know exactly what those blocks are. But it's not as big an improvement right now for people who are running their own network, because if you're using, for example, a subnet EVM, or in the future, if you're using Hyper SDK, you're not going to hard code those blocks, those little checkpoints into those VMs. And so another optimization that we can do to get the exact same parallelization improvement is to actually include a Merkle tree where the key value pairs are the height to accepted block hash mapping. And this enables us to get a very succinct proof of a block hash that is accepted at any given height. So you can, for example, sync this entire Merkle tree. If you just get, for example, block in, then that would include the Merkle root of the height to hash mapping for all of the accepted blocks from height 0 all the way to height n. And so by syncing this Merkle tree, you can choose exactly arbitrarily which block height to fetch from. So you can parallelize arbitrarily from there. So this actually has a lot of other nice properties, but one of the things that this will enable us to do is for arbitrary networks that don't actually encode their own checkpoints, they'll also be able to get the advantage of parallelizing fetching in the exact same way without hard coding those checkpoints. The other nice thing about this is that it also gives you this really succinct Merkle proof of any block that's accepted in your entire history. So we've also started to explore a little bit about what the light client design should look like for the Avalanche network. And it's already really pretty nice because we have this great, we have the P chain, which enables you to connect anywhere on the entire ecosystem, where once you've synced the P chain, you actually already have the validator set of every network that's out there. And so you can already verify, let's say we haven't implemented consensus proofs yet, but once we do, you'll already be able to verify a consensus proof of the last accepted block of any network that's out there by just getting a BLS multi-signature for it. And from there, if that does include this Merkle height to hash mapping, you'll actually be able to get a succinct proof of any block in the entire history, which is really nice because the way that light clients work today is if you want to get a proof from an individual block, and a lot of information typically gets encoded in these blocks. In the EVM, you might have information like a transaction inclusion proof or a transaction root is included in the block, or also a receipt hash, which includes information that you can prove the events that happen there. You'll also be able to do this with a succinct proof for any block in the entire history. But the way it works now is you get one, like the latest block, and then have to traverse all the way back from there to whatever block you want the information of. So you just do this in a linear process. By switching to putting this into a Merkle proof, we'll take that O of n and then turn it into O of log n. So it'll make it much, much more efficient in order to fetch arbitrary blocks and get inclusion proofs about that. Nobody else has done this yet, so this will be a really nice thing to make light clients more practical and more efficient on Avalanche. And the really nice part will be you basically just connect to the Avalanche P chain, and you can immediately connect to anywhere else in the entire Avalanche ecosystem. So you end up with a really nice, clean, and simple design. And by combining that with this height to hash mapping, it's more efficient as well than any other light client implementation that's out there so far.
It also works pretty well in like a world where you want to have validators delete historical blocks, because in order to actually add new entries to this Merkle mapping, you don't actually need the full historical Merkle mapping, because you're always adding new entries to essentially one edge of the tree. So either left side or right side, depending on how you encode your heights, but you'll always kind of keep that as like an ever growing entry. So you can essentially just keep the Merkle proof of the previous height. So it's very efficient from that perspective as well, even in a pruning world. So it's pretty nice.
Yeah, it should end up being relatively small as well, which is a good thing, because I talked with Dan about implementing this in the Merkle DB, and he was like, I don't know when we're going to get around to doing that. And I was like, I guess we don't need that, because that's like a really, really nice part of the design, is that you get this very succinct thing to have like a validators don't have to store the entire thing. But it's also really nice because it really shouldn't be that large either. It shouldn't make a dent in the size of state in total. So we can sort of implement it now using the full Merkle DB and just consider it part of the state, and clean it up using that really nice, like very natural optimization later, where we don't even have to have any sort of state rent or state expiry scheme in order to clean up. You can just always clean up very easily and have a very succinct commitment to it, which is super nice.
Yeah, I mean, a lot going on in the like consensus area. I think this is probably the more less discussed, like more actively really developed behind the scenes stuff, where like you as a user or like someone building on subnets doesn't really know that this is going on, but this is the painstaking, like very little applauded work that keeps the lights on. And so this is stuff that we'll obviously continue doing. And someone actually reached out to me and said, it was surprising you guys included tech debt maintenance or like, optimization kind of work on your roadmap. I was like, well, it's at least a third as important as all the other stuff that we're working on. Like it doesn't matter if you have cool stuff if it doesn't work all the time. So we're trying, nothing to guarantee that it will work all the time, but definitely like we need to be explicit about focusing on that work. And so no better place to communicate that than our view of like how we should be focusing on this stuff. So I think that's enough for this. I think we should go into the ACP world. So there's been a lot of ACP stuff that has come out in recent days, really from Aaron and Michael, actually. So we'll first actually go right into Michael, your discussion post, and then we'll round it out. Give me 1 second just to share this. Let me know if you want me to scroll or like focus on a certain part, but this is a fun one.
Yeah, let me provide some context first, I guess. So Warp messaging launched as part of Durango, as you all know, on the C chain anyways. And we are super excited about its design and possibility for what it will enable going forward as far as subnet interoperability. A lot of what Aaron was already talking about depends on these BLS multi-signatures that Warp kind of lays the foundation for. At its core, Warp works by validating these BLS multi-signatures in the sense that a threshold of the sending chain's validator set must participate in the signature in order for it to be accepted on your given destination. That's really great in the sense that it scales well as your validator set grows. So if you start off with a smaller validator set, obviously there's fewer participants in those multi-signatures, but as it grows over time, you don't want to have to depend on some like central trusted entity as far as performing all of your cross-chain operations, and that is handled by Warp inherently. But in the case that you have a small centralized validator set, you might want to extend or improve the practical security of those multi-signatures beyond just the validators of the chain. And there are a number of reasons for that, mostly taking into account the most common or most frequently referred to use case of cross-chain messaging, which is just token bridges. So you can consider a case where you launch a subnet. It's a relatively small validator set because you're just getting off the ground. You connect to the C chain to bridge in tokens using Warp and using Teleporter, which should be very easy to do now that both are live on mainnet. Now you gain some popularity, say a few $1 million goes over that bridge. It's locked on the C chain. It's minted on your subnet. Now those validator BLS keys have the capability of signing messages to redeem those few millions of dollars that are locked in the bridge contracts. And on a theoretical level, it's great that it's as secure as your chain is, in the sense that it's still just an honest majority of validators of your chain that are required. But if we're talking about a very small validator set, you really might want to increase the practical security of it, particularly when considering, even if a safety failure were to occur on that chain, you could always reach social consensus and fork back to state prior to that safety failure. If your cross-chain application gets exploited, you're far less likely to be able to ask the C chain to perform an upgrade just for the sake of your subnet. So that was kind of the founding point of, or the starting point that we were thinking on of, we have this great cross-chain model. How do we make sure it's still secure even in this small validator set case? And the core of some of these ideas are really just, let's add more parties into the mix that can have higher or more well-established security reputations. How to go about doing that, we are still actively discussing what might be the best route. So there's a few options that I outlined here in the ACP discussion. By no means are they final or necessarily even good ideas, but I think it's a good starting point to think about. So the first option is at the node security level. So as a validator, right now you have this BLS key on your disk. Your Avalanche Go node uses it to sign warp messages. As Patrick pointed out, it also is used for a few other things that get in the way of this idea or cause complications for this idea, but let's ignore those for now. If you register your BLS key on the P chain using the add permissionless validator transaction, and you provide a proof of possession showing that you do in fact own the private key for that given public key. In order to strengthen the security of that individual public key that you registered on the P chain, one way to do it would be to make that public key be the aggregation of multiple private keys that are kept in different locations. And you could do this for your individual node if some other service were providing this warp observer functionality. So what the other service would do is just run a node for your chain. It would not be a validator. Have its own BLS key. It would publish its BLS public key. And when your node starts up, it would register, or you would register your node's public key as the aggregation of this known public key and the private key that you generate on the node locally, such that when your node is queried for its warp signature, the way it is able to provide it is by first querying the observer it's configured to use, getting its signature, and then aggregating that with its own signature, which makes it such that even if your node is compromised, even if an attacker has full access to your node, they can't forge warp signatures from that given node. This is totally hidden from the P chain in the sense that the rest of the network just sees that your node has a BLS public key. It doesn't know how you're securing that necessarily. So it improves the practical security that you know that you're using this service because you're the one running your node. No one else is able to see that. So that's definitely a trade-off there. The other possible option, which would involve network changes, is to explicitly register keys that are required to participate in a warp signature on the P chain. That's option 2, if you don't mind scrolling down, Patrick. This would require some changes to the P chain in order to really alter the warp protocol on chain and explicitly add keys that are required to participate into a warp signature. And during the validation process, you wouldn't, the destination chain wouldn't just be validating that 67+% of the stake of the source chain participated, but it would also validate that in addition to 67% or higher of the source chain stake, also these explicit keys must have participated. And those would be, trusted observers in this sense again. So there's plenty of questions here. Who the trusted observers are is definitely a big one. My thinking was that this could really be offered as a service. So you could have companies that are in the blockchain infrastructure space that have good security track records participate as observers. And I'm not sure how that dynamic could work. But the idea being, let's add in additional keys that are required to produce these messages, such that even if you were to corrupt, say, hypothetically, 7 of 10 validator nodes of a given new subnet, you wouldn't be able to forge a message from it. Since posting this, had a few great discussions with Aaron also about other options that I'm not sure made it onto the discussion thread just yet, but they involve really what all of this boils down to is kind of a combination of proof of stake and proof of authority model. Aaron, do you want to? I think that.
I actually
is this the right comment, or is this a different comment based on what you?
This there's not a comment for this one yet. I told the legal team I would not discuss it in public yet. But that's okay. That's okay. Yeah, for the ones for this comment, one team that we've worked with a bit and we've had great experience with is Cubist, And so what they've actually done for Ethereum is they've designed what they call a virtual HSM, which will actually secure the key for Ethereum staking and signing inside of this VHSM, and will guarantee for you that the HSM enforces you won't end up double signing 2 blocks of the same height. So, this post sort of breaks down like how they do this for Ethereum and what that might look like for Avalanche, which ends up being a little bit different. And for Ethereum, the only property that they want to maintain is that they never want to double sign at the same height. They want to make sure that they're not going to sign conflicting blocks, because if they do, they get slashed. Right. And so this is something where, a correct client shouldn't cause you to double sign 2 different blocks at the same height. But if you're an operator and you're putting a large amount of stake behind this, you might be concerned that the tail effects of there might be a bug in a specific implementation, and it might cause you to actually sign 2 conflicting blocks, which could slash your stake. So this is, slashing risk that comes out a decent bit, which obviously you want to mitigate. And so what Cubase built was this virtual HSM, which will, internal to the key management tool, the VHSM itself, it will verify that when you send it a request to sign a block, that you have never signed a block that conflicts with it before. So this does require that you actually maintain a small bit of state within this sort of trusted environment of exactly which blocks you sent a request to sign in your entire history. And it does this inside of AWS using a mixture of AWS KMS, DynamoDB, and a couple of other, or AWS Nitro as well. But by doing this, they can guarantee that assuming within this certain threat model, assuming there's no compromise, you will not, even if there's a fault in your client that sends 2 requests to sign for the same block, which again should not happen, so this is defense in depth, you will not produce 2 conflicting signatures. So this provides another degree or another layer of defense against slashing risk for Ethereum. And it relies on the ability to say, when you send me a stake or a signing request, I can perform this check that it doesn't conflict with anything that I've signed before. So this works out really nicely. It adds some practical security to the key management, and it also enforces this additional check. So for Warp, it ends up being a little bit different because for Warp, what we have to worry about is that the ways that we're using this key is a little bit different and potentially harder to enforce the requirements that we have. So if you want to perform a similar level of security, you have to move a little bit more into the VHSM, which is possible to do. And so this post just breaks down what are the different trade-offs of what you could put into the VHSM and what are the trade-offs between those options. So the first option would basically just be, well, we'll put the key in the VHSM and we'll send the request to sign it. And when we do that, it'll send us back the signature, right? And so this provides no theoretical improvements in security, because if the node which previously just held the key is compromised, you can still send a staking request in the exact same way. And if it's not performing any of its own verification, it will sign whatever you ask it to. So the interesting thing about it is there's no improvement whatsoever in theoretical security, but from a practical point of view, there can be a significant improvement in security. Because when you get onto a device like this, you probably have to look around or run some script. And actually, Michael was just telling me yesterday about, you can actually have honeypot onto your machines as well, to say, if somebody just does some command like cat this key file, or is just looking around in a way that you wouldn't expect to do in production, what you can actually do is sort of automatically disconnect it from the VHSM. So there's a lot of practical security improvements that you can make to say, make sure that, if somebody logs onto this device and sends a non-standard looking request to it, which would look like somebody snooping around trying to send an invalid request to the VHSM, you can kick them off very quickly. Additionally, if you do take over a machine like this, which should not happen in the first place, obviously, right? But if you do, you might not know what to make of this key. Whereas if you're looking at Avalanche Go, the format, it's a standard location where the BLS key would be stored. So you might know to, yeah, it's fine. Either way. Sorry, I got distracted by that comment. Michael, I'll just say this part out loud. Michael points out these don't work as great if people know that they're there. So I guess I wasn't supposed to say that in public.
What we really got to do is you start putting BLS keys there, and then if people use that.
No, Patrick, you weren't supposed to say that. Yeah, I guess that's the whole mile now. But yeah, so there's a significant improvement to be had from this practical security improvements. But anyways, it doesn't actually provide any theoretical security. And if we do want to get a larger improvement, what we'll have to do is actually authenticate what is happening inside of the VHSM. So one thing that we could do here is to enforce that we won't sign messages that come from the same height if we've already received a request in the past, to say that if I already signed messages for block height 10, if you send me another request for messages signed at block height 10, I won't do that. I won't actually honor it. But because the warp message format doesn't include anything about the height, if I want to convince you to sign some arbitrary message im, I can just pack that into the next block, right? And then say, hey, I want to ask you to sign this. And so if I said, I don't want you to be able to sign a given message, I have to actually authenticate or verify the entire flow, including the state, or verify the whole block to make sure that that message is something that could have actually happened and that I haven't signed anything that conflicted with it in the past. So what this basically amounts to, and I outlined this in option 2, is to keep the entire blockchain inside of the VHSM and verify each block as it goes, so that any transition that you're asking me to verify is something that I could not totally make up. So for example, the example Michael and I were talking about yesterday is if Michael has $100, I could send, or let's say Michael has $0. If I have total access to the device, I can say, well, Michael sends $100 to Patrick on some other chain. And because you're not verifying the state transition, you could just say, yep, Michael might have had $100. So I'll just send this around. But if I'm actually verifying the full transition, then I actually can't send the HSM this invalid thing unless Michael actually signs some transaction that makes that possible. I might be able to order the transactions and order the execution to change the outcome. But as long as you're verifying the entire flow inside of it, I can't lie about something being possible when it wasn't actually possible. So essentially, I can't make up something that couldn't have possibly happened unless there was a transaction that would have authorized it on chain. Additionally, if I'm tracking what blocks were sort of executed in order, then I also can't tell it to do two different things, right? So if I say, well, Michael does actually have $100, and then I send one message that says, well, Michael sends that $100 to Patrick, then if it's already processed that transition, I won't be able to say, well, now Michael sends $100 to Steven, because it will only process that once. So it essentially prevents this kind of double spend version of things in this multi-chain.
The one nuance I'll throw here, which is kind of extends what you're saying, but also summarizes a bit of what we were talking about yesterday, is like some people think that in a world where it's like Starks are dominating everything, which would be great. Like if you can generate Starks in like 100 milliseconds and then verify them in like 100 milliseconds, the world's going to change in a great way. But like, nonetheless, even if you have that, you still need to have some mechanism to enforce that whatever proof was generated was actually the agreed upon proof. So in the world of like a rollup, you typically have a dedicated sequencer that can post these proofs, and you assume that they're not going to post conflicting, or like whatever is posted becomes the proof. And that's typically how they work. But in a world where you're using, like, let's say this to represent like verification results on a remote destination, like another subnet, you can't just say like, well, if some proof was posted that was valid based on some set of state transitions you concluded, you don't know that that was actually the state transition. Like you have to somehow either incorporate the consensus output into the proof itself, so like that the result is monotonically increasing and that a superset of validators have actually authenticated that, or that you actually sign that with some sort of messaging mechanism like this. So some people have also asked us, like, in a world where you have like domination of Stark by Stark and Starks, like what does that actually look like for this warp messaging? It's like, well, actually they're not necessarily redundant. You still need abstractly like the ability to attest from some remote consensus region what the actual consensus result was, regardless of how you want to like communicate some sort of message or add additional security around the actual verification of that data, if that is a full state replay or something else. And I think the big question that we all have to ask is like whether or not in the end game, as people say, like that every chain will actually be verifying the state transitions of every other chain, or if they will instead rely just on like entities from that region attesting. And I think that at scale, that's becomes the big question. So I think this was a good one. I think we still have a little bit more time. I think we should cut over to the other conversations around the P chain stuff, because I think that those are so interesting, and I want to make sure that we get at least touch on those.
Yeah, I see there's also a question, which I think is somebody promised they'd ask on Twitter, so I want to bring it up. But Ravindra says, I promised I would ask, but when benchmarks for VRIX, and also is Firewood faster than MerkleDB, or can I give Ron a hard time? So Patrick, I'll leave the VRIX one to you, but I just want to say you can always give Ron a hard time. Always.
So yeah, we'll work on that transition when we talk about that. But the benchmarks for VRIX are coming along great. I'm not going to share any information here, but if you do look around the GitHub, you will see me posting status updates. The point here, as I mentioned at the beginning, like I only focusing on like distributed DevNets, not like local or single cluster or whatever. And so I only optimize in that setting and just working on getting things reliable, but having a single script that anyone can run to fully reproduce the results. So coming along, my target, and I can't believe I'm actually saying this here, but like my target would be end of next week to have that posted for you to reproduce, and I'll share my results with some analysis of what that looks like. But we will see.
Cool. Yeah, for discussion 68, the idea here is a step towards subnet sovereignty and improved developer experience. So the discussions around these ACPs have been ongoing, and I've started to work on breaking them down into more individual changes that would lead to this overall result of, as we talked about last time, reduce fault isolation, reducing the economic constraints on the creation of subnets, and allowing subnets to have greater control of managing their own validator set, leading to, as we talked about, greater sovereignty and improved developer experience. So the first one is up as a draft PR. It's number 73, if you want to bring that one up, Patrick. Also want to point out 73 is, there's a link, or it's not on the discussion, there's a draft PR actually. I just took that one from...
Sorry, 1 second.
Yeah.
You're whipping out these like ACPs so fast that it's been tough for me to keep track of the conversations and discussions. So that also, before you get into this, there's a lot of really interesting and deep conversations going on around like what are potentially very large changes to the architecture of Avalanche. So if you have thoughts about that, now's the time to jump in and communicate, discuss. Like, it's an open platform. You got a GitHub account, you can chime in. And so please do so, because, you know, I think the community sometimes is, I haven't seen this in like Avalanche community, but in other communities I've seen it happen where someone's like, oh, how did this, like, you know, decision, or like, why are we doing this? And they like just neglected to participate or pay attention for the past, I don't know, like 2 years, when like a conversation was going on about a particular direction that like the platform or like whatever network was going. So it's not a valid excuse is what I'm trying to say. So if you want to contribute and talk about it and like raise your concerns or like express your support, this is the place, this is the time. So just want to reemphasize the importance of like what this mechanism is supposed to be for, and hopefully the community, you know, finds use of it. I certainly have gotten a lot of great feedback on different things I've posted, and I think a lot of other people here have also felt the same.
Yeah, 100%. So with this one, ACP 73, also if you could scroll down before the actual details, this is 73 is the best number. That's the words of Sheldon Cooper, and there's a great link partway down. I see Patrick's given up on actually scrolling to it, but if you pull it up and find it, there's great slides on why 73 is in fact the best number. So hopefully this is the best ACP as well. Anyways, the idea with warp address transactions is to enable any pair of a blockchain ID and address on that blockchain ID to send a verifiable message to anyone else. So it's enabling a transaction in of itself to have an address derived from a warp message. So warp already enables you on subnet EVM to send a message that includes both the source chain ID, network ID, and then finally a source address, the 20-byte address on the EVM. And that source address is actually an arbitrary number of bytes, which means that, you know, it will actually work or can be forward compatible with things like the Hyper SDK, where those addresses may have different lengths, or any future VM that wants to have either a variable or fixed length address of a different size or format. And the idea with this is to enable that to be treated as an address capable of signing transactions on any other blockchain. And this is geared specifically towards enabling subnets to send transactions directly to the P chain. in order to enable them to manage their own validator set. So all building towards the subnet-driven validator sets that we want to enable. And the idea is essentially we're going to have this blockchain ID address pair serve as an address on the P chain in the exact same way that you would use your normal Bech32 address. And this would basically take a hash of, it would take a hash of the blockchain ID and then the actual address that's sending it, which again on the EVM would be that 20 byte address, and then take the first 20 bytes. We're actually going to copy, or at least this the proposal for doing this on the P chain is to copy the exact same format we currently do with SecP keys, where we take a ripe MD160 hash of the SHA-256 of the full public key in order to calculate a 20 byte value, and then just treat that as the address on the P chain. The reason for this is to make it blend directly into the existing P chain implementation, which again has these 20 byte addresses. And we just want to enable any address on any blockchain to create a transaction that can be interpreted by the P chain in order to, again, authenticate and verify some message that enables it to update a validator set on the P chain. So the next part of this, after warp address transactions, once you have the ability to have any address send a transaction to the P chain, you want to actually master what is the flow going to look like for an on-chain program on some arbitrary subnet or even on the C chain to send a transaction to the P chain and then actually generate that transaction, issue it to the P chain, and confirm that it's been accepted. So this is in discussion 74 that I've laid it out. And this is just sort of brainstorming what that might look like in order to make this practical. Because there's a lot of concerns and changes that come up when you want to have an on-chain program actually define this entire flow. You have the question of once it's no longer a user involved in the loop, you have, should it be upgradable so that you can, for example, if the P chain changes and there's some new feature that you want to support, so you can upgrade your contract in order to use it, in order to use that new feature. And so discussion 74 goes through a couple of the different options that outlines how we might make the P chain transaction format easier for on-chain programs, as well as what we would need to do in order to make it possible for these on-chain programs to verify when their transaction's been accepted. Patrick, do you want to bring up discussion 74? Yeah, this one. So this will walk you through all of the different models that we might have. Currently, the P chain uses the UTXO model. So I put in a little explainer here of what the UTXO model is. Then there's also the account model, which is what we use on the C chain and the EVM typically uses. And the UTXO model requires that you specify all of these individual inputs, which for an on-chain program could actually get fairly difficult to manage when the only requirement that they really have is that they have the authorization to send a transaction to the P chain that updates this validator set. The account model, similarly, you have to manage the fees that are going to be put towards sending a transaction to the P chain, as well as making sure that that is in fact the account that's allowed to sign it or update a validator set on the P chain. And so what I went through here is, okay, well, here's the UTXO model. This could end up getting fairly complex to do full UTXO selection in an on-chain program. The account model could work a little bit better, but you would still need to handle the fees to pay transactions on the P chain. And so if you scroll down, what I ended up coming out to was defining some sort of account abstraction for the P chain at a high level, where currently, in order to generate a transaction on the P chain, you actually have to sign the entire transaction hash that includes all the inputs, outputs, the full transaction specification, where what we actually want the on-chain program to authorize is very particularly a subnet validator set update, as opposed to specifically which UTXOs would be sent, what outputs would be sent, et cetera. And so the idea here is to say, well, instead of signing all of that and having to sign up for, I need to be able to handle UTXO selection, account selection, all of these inputs, outputs, all the different transaction types in the P chain, which could be hard to make forward compatible, to just define one more generic format for what a validator set update ought to look like. And then say, we'll sign explicitly just that, including a nonce as well, so that you can't sort of double spend these validator set updates. And then to wrap those with an outer layer transaction to be issued to the P chain. And by doing this, we can greatly simplify what the flow will look like. You won't have to worry about input selection, inputs, outputs, or all of the different transaction types. And we can allow the on-chain program to only specify, well, here is the type that I actually want to send. Here is what I'm actually trying to, here's the validator set update that I'm trying to perform. And then leave everything else off chain So including the wrapping that, having a relayer to actually send that transaction, which could either be a centralized off-chain relayer like we use with Teleporter, or it could be all of the validators competing to just go ahead and send a transaction as quickly as possible, delivering it, along with the memo field to actually say, well, who is the person that sent this update? So I can try and issue some reward when I get it back. Now, after we've done this account abstraction, we hopefully have the ability to send a transaction to the P-chain in a format that's very, very easy for an on-chain program to understand what that update should be, what it should look like. And this is just a really rough draft of what it might be. We want to make this as generic as possible so that it's just, ideally, you'd just be sending a diff set of what I want to update on the P-chain for anybody to be able to read. And then after that, you need to be able to verify that update. So if you scroll down a little bit, I also have some notes about how we would add an event route essentially to the P-chain in order to get a transaction confirmation. Where most likely what we'll have is taking something that looks similar to the receipt hash in Ethereum, where an individual block would include some root hash, where that root hash is, again, a Merkle tree of some key value pairs, where, for example, if you wanted to prove a specific transaction was included, the key value pairs would be transaction IDs to, or would just be transaction IDs or transaction IDs to the full transaction details. So that if you want to encode exactly what the update was, you would basically specify, well, here's all of the subnet update operations, encode them into a tree that you can then verify on your recipient subnet. So as soon as you have some consensus proof, and Josh is working on an ACP to define how consensus proofs ought to work on Avalanche, you'll be able to say, well, okay, this block was accepted on the P-chain. Here's the event route. And then you'll be able to supply a Merkle proof of this subnet operation that is, or subnet update operation relevant to you just happened. And so you can then update your validator set and know the transaction was confirmed before issuing any subsequent operations. So yeah, that's the breakdown of how on-chain.
Everyone got it? All right.
Yeah, I mean, I could talk for hours. I guess, like, as far as the transaction confirmation step, like, this very much assumes that you're running a light client of the P-chain, which feels to me kind of odd in that, like, the whole design of the P-chain subnet architecture, right, is that you have the state of the P-chain so that you can efficiently verify warp signatures from arbitrary numbers of subnets, right? But if you're running a light client of the P-chain, you explicitly don't have that support. So what you essentially need to do is then get Merkle inclusion proofs for any validator set that you're, that you need on demand, right? Which just kind of like increases the cost of verifying those signatures in what I would assume to be pretty non-trivial, especially if the actual state size of the P-chain is expected to be small, which it is. So I guess I don't like I think that the consensus proofs are super important for a bunch of other things, but I don't necessarily understand why we would care too much about the Merkleization and like having your Merkle inclusion proofs in the recipient side of your warp message. Like, does that make sense? Or
Yeah.
I guess what's the intuition, or what's your rationale on like why that's important?
This is really just, again, to make it more forward compatible of like, well, you could just say this is already, if you have the full read replica of the P-chain, you could just say, well, this has now happened. But if you wanted to say, well, in the future, we might want subnets to be able to run with a light client of the P-chain as opposed to the entire state, this would just make that like possible. But that's a very good point that we currently have the full read replica of the P-chain, so that's not necessary right now. I guess one question, that's definitely a great comment to put on this. So can you put that comment on this after this call? But secondarily, I wonder if there's a great way to sort of blend the two where we can use the full read replica for now and still very easily support switching to the Merkle proof in the future. Where, for example, maybe we don't have to modify the P-chain format now. And this could be handled by like your proposer VM version of the client that just tells you whether or not a specific operation has been included at a proposer VM height. Or actually, I think this is fairly easy, not necessary.
I mean, like the P-chain is going to have a Merkleization of its state, right? Like, if only for state sync purposes. Like, we're certainly going to need to do that. I guess the key thing is whether or not we would want to optimize for inclusion proofs in that design, because there's certainly a push and pull of the efficiency of the Merkle tree versus the efficiency of the proofs produced by the Merkle tree. So, as you're willing to introduce more and more moon math, the Verkle trees, provide this nicety where you have these incredibly small inclusion proofs. And then, you have binary Merkle trees, which is maybe a middle ground. And then you have, a bigger Merkle, like a bigger branching factor, which produce very large inclusion proofs, but is perhaps much more performant on the actual execution path. So I think at the end of the day, this is basically a question of like what we would want to configure the Merkle DB as, because again, the branching factor in Merkle DB is just a config. So whether we would run a binary Merkle tree, a 4 branching factor, hexary, bytewise, these are all very easy to configure, but once they are configured, they're not easy to change. So it's definitely something that we would have to consider on like what exactly our goals are for the Merkle tree, because up to this point, I've definitely been primarily excited about the Merkle inclusion, or the Merkle tree inclusion for state sync specifically. And I have a whole manifesto on why I think full syncs of chains is stupid. But we don't need to go into that.
All right,
but
we're going off the rails. We're going off the rails. We should do a quad kilo branching. Have you ever heard of 4096?
No, trinary, ternary.
No,
trinary,
quad
yeah.
kilo.
No, trinary.
Right,
Perfect. We'll make our own hardware. Sorry.
So because the Merkle DB is configurable, we can have like the state can be like very, very wide branching factor. But if we were to include inclusion proofs for like let's say there's a maximum of 1,000 operations inside of a block, we could configure those to be efficient for Merkle proofs as opposed to for like long-term storage. Right. So there's 2 different Merkle trees that we're talking about here, because one is like long-term storage state, and then a separate, like, we can optimize them for 2 different things. But either way, I don't think we actually have to do this as part of the P chain, because we can have the proposer VM / P chain combo. Like, it's going to be a read replica anyways. It's just a question of whether it's a light client verifying it or having the full read replica. But all we have to do is have the ability to serve a request that says, has this subnet update been included at this point in time? And if the answer is yes, then we say, okay, great. We can send this message to an on-chain program that says, yes, the subnet update operation is valid. And that can start out with, yes, this is valid because we have the full read replica. And in the future, without changing the underlying VM itself, only changing the platform VM, we can say, well, now it's actually going to use a light client instead. So I think these can actually be decoupled. And we can just use the read replica at first. It's easy enough. And if we wanted to optimize it later, we could without changing the underlying VM.
As much as I want this to keep going, we should probably wrap things up. Let this be your intro to some of the open discussions. If you're interested or want to talk about it, chime in. Very much an open conversation right now. So usually if there's enough interest, we'll do, dedicated kind of hangouts, meets with everybody to talk maybe more through some of the ideas. But if you have any questions, ask them. If you have any comments, post them. So thanks everybody. Michael dropped off for an interview, so just us now. But thanks, Steven and Aaron, and then thanks everyone for sticking around. So.